Hi everyone, today we're starting a series of videos trying to better explain the technology behind the Tuki protocol and what makes it scalable, decentralized and secure. The Tuki protocol is a second layer solution that effectively offloads transactions from a distributed public layer 1 blockchain like Ethereum, a Turing-complete blockchain, to a layer 2 which is built out of users' web browsers that come together to form a decentralized network per campaign or per contract, and that decentralized network of browsers is able to interplay a smart contract between them, state mutating and progressing the state of the smart contract in a scalable manner. It's just the browsers, so it's a decentralized browser network. Each browser is a decentralized distributed peer or node in this network, and it's able to propagate the state machine of the smart contract without touching layer 1. Okay, so the basic idea is that these browsers allow themselves, using the Tuki protocol, to progress the state. So only by using web browsers and link sharing between people, we can forward the state of the smart contract in a secure manner, in a cryptographically secure manner, that is proven to adhere to the rules of the smart contract, yet in a scalable manner, since only browsers are interacting with each other, there are no servers involved. And of course, it's decentralized because, well, these are just browsers acting out, and each browser is a different user, so by default, it's decentralized. Let's see more in depth how it looks. Actually, the state machine of a smart contract is a lot like a tree. It always starts with some contractor initiating a campaign or a contract. For ease, we'll basically go with an example, and we're going to use the Tuki network use case for this. So you can all go to test.tuki.io, our Robston testnet, and try and create a campaign. And we can think of this example. Let's say this is a yoga teacher, and the yoga teacher is trying to reach out and find new students. Okay, and he's going to try to do this with social sourcing. So when this contractor, this yoga teacher, initiates the campaign, we are going to touch layer 1. So the creation of the campaign contracts do issue transactions directly to layer 1. And that's a good thing because we're a layer 2 solution, we're not layer 1. We actually want the distributed, globally social secure manner of a distributed virtual machine with tens of thousands, hundreds of thousands of consensus nodes. But its social security of the layer 1 also makes it very slow. So we want to gain the benefits of layer 1 without needing all the transactions on the contract to run on layer 1. And that's the base notion behind it. So the contractor does touch layer 1 to make sure that the contract is saved on the public immutable blockchain. Since this browser network, it just runs for the lifetime of the contract. You can think of it as a sort of ad hoc blockchain shard just for that smart contract. Once the contract resolves itself, all the basically finality states will be cryptographically proven and saved back to layer 1. But the whole idea is that for running it, while it's being run and referred to maybe millions of people in very large campaigns, all these transactions don't have to rely on layer 1. So we're saving these transactions from running on a slow blockchain. They can run at the speed of HTTP just using web browsers, completely scalable. Yet, eventually we get all of it persisted and adherent with a really decentralized, really globally secure blockchain. These are the great benefits. So what happens behind the scenes is when the contract basically is created, the contractor also issues a secret that only it knows and basically puts it in the Tuki link. Also, we save to IPFS a code hash, and behind the code hash there is the JavaScript code and TypeScript code that's required to make each of these browsers a decentralized node. So when the contractor, this yoga teacher, shares the link with his current students, let's just say he has 10 and he wants to gain more students. So each of these students receiving the Tuki link and pressing on it, their browser will immediately, since the Tuki link contains two things, right? It contains the code hash. With the code hash, the browser goes to IPFS and retrieves the JavaScript and the TypeScript required to fulfill the Tuki protocol. But it also received the secret, what we call the state hash. It received the secret in the link from the contractor. Now, let's go here more into zoom into what happens inside the node. So after receiving the code, okay, so giving IPFS the code hash, then receiving back the code itself, the JavaScript and the TypeScript, of course, all the solidity of the smart contracts, etc. We do two main high-level functions. First, the browser is able, with this 2-key protocol code, to validate the hash that it received in the state hash. So we can validate that the secret sent by the contractor was indeed the secret of the contractor, since all of the public assertions regarding these secrets are saved on IPFS. But then, if this guy wants to, let's say he gets a 10% maximum referral reward and he wants to make a stateful transaction, he wants to say to the contract, okay, I want to just take 2% and I want to pay forward 8% so that there's incentive to pay it forward more and more to find the next students. That's a stateful transaction. But the browser then allows the student of the yoga teacher to then mutate the hash to generate a new state hash. Now the beauty of this is that it's all done within the browser. So the browser knows to validate the hash and then to mutate the hash. And what happens is that then the student can share a new hash in its 2-key link. So basically when this next guy, the friend of the student, layer 1 friend of the student, receives the 2-key link, it receives it with the same code hash. So the browser, this guy's browsers will do exactly the same thing. Go to IPFS, request the code, it will be exactly the same code. That's what makes all of these actually creating an ad hoc, so to speak, blockchain shard, because they're all running the exact same piece of code. Okay, so of course this browser will download the exact same code using the exact same code hash, but what will be different here is the state hash. The state hash that this browser will receive will no longer include the secret from the contractor. It will include the secret of this guy. And then, with this secret, it can only prove that it came after this guy. It can actually never prove that it came after anything else. So the state hash that you receive in a 2-key link basically positions you inside the state machine of the smart contract. That's the beauty of it, and it's cryptographically proven. Since this is like, you can think of it sort of a recursive zero-knowledge mechanism where each party progresses, but only by knowing the secret of whoever sent you the link. And this way, basically, an entire chain of transactions, even if they're state-mutating transactions, can be basically propagated from browser to browser to browser, but actually not required to issue any transactions to layer 1. And it's all because the browser knows how to validate the hash it receives and generate a new hash. So if we count the state hashes, basically, or the secret sent, that the contractor sent, let's say, secret 1 to this guy. This guy eliminated secret 1, put secret 2 inside, and send it along here. Of course, this secret 2 already contains all the state-mutating information that he did. For example, taking 5% and paying forward 5%, etc., or doing any other thing in the contract. And then basically, this guy has the next secret, this guy has the next secret, and you can only prove that you came after the last person just because you only have the secret of the last person who gave it to you. This is how the state progresses without requiring to touch the first layer. Now the beauty of it is all these states are actually saved within the chain of secrets, basically chained together, but the secrets are of course never shared, just their public assertions are. So basically then we can interplay this entire contract off-chain, and whenever we want, offload these proofs, since each person here basically can prove that he came there, but also contains the proof of the chain. You cannot mutate the chain, so you cannot basically kind of hack the chain after you get there, but you can then report it back to layer 1. So whenever we want, it can be once a day, once a conversion, whenever it's convenient, we can basically then persist or save the entire state machine that was run off-chain into the layer 1. So we're still basically getting the entire security here, cryptographic security, that the smart contract rules were maintained. We're eventually getting persistence to layer 1. We're actually getting more decentralization because, as opposed to, when you want to do transactions with layer 1, you actually need to rely on layer 1 servers. Right? Like Ethereum nodes, which are servers, no one runs them on their browser. or you need a dedicated server. You basically go to Infura or whatever. Even a lot of centralized providers are on there. So you need master nodes of Ethereum to relay transactions, mine transactions, broadcast transactions. Here you don't need anything. It's just browsers, network acting for browsers by the browsers. So it's actually even more decentralized than layer 1. Then of course it's completely scalable because it's just browsers. So it's just HTTP in the browser itself. It doesn't rely on any Plasma node, Ethereum node, or backend node for managing the state. And it's secure because of the cryptographic assertions along the chains. So this is how version 0, or we call it version 1.0 of the protocol works for multi-party state chains. In the next videos, we'll cover how we generalize this protocol to maintain multi-party state network, which means how do basically cryptographically sync the state of one chain with another chain. And this is, in terms of development, it's a gradual process. We're going to introduce it in gradual steps, and we'll cover these in the next videos. Thanks for watching.